symmetrical induction machine, which means that we will try to find a differential equation that describe the electrical part and the mechanical part of the machine. So this will pave the way later on to design the vector control for the induction machine. So let's start with modeling. Of three-phase symmetrical induction machine. Now simply, if I assume that any three-phase has stator and has a rotor, and three-phase, so I'm having three windings. So simply, this means that I can put the first coil, let's assume that this is the first coil, here. Now, the second coil will be distributed 120 degrees in space, let's say. Let's assume it's here. And the third one, after 120 degrees, let's assume it's here. Now simply, let's assume we are also having coils on the rotor. Even if we have a square cage with no coils, in the end of the day, it will be identical to what? To a coil that's distributed in space by 120 degrees. So for that, let's assume that we have this coil here for the rotor. This is the second coil, and this is the third coil. Let's assume those are Y connected. And if it's square cage or wound rotor, I will short the terminal. So this will be the rotor that I'm shorting what? I'm shorting the terminals. Now let's assume that I will energize the stator. So this will be plus minus VAS. A current will flow here, IAS. The same thing here. Let's assume that I will energize the coil by plus minus VBS. A current will flow, IPS, and the same thing for the phase C. So plus minus VCS, and this will be the ICS. So here, this will be the AS, this will be the BS, and this will be the CS. Now here, S stands for stator. In the same fashion, this will be the AR, this will be the BR, and this will be the CR. And the rotor is rotating by which speed? By omega r speed. Yeah, omega. Omega. The synchronous speed is something else. The synchronous speed is fixed speed related to the frequency. Now the rotor is rotating by which speed?
Omega.
By the physical speed of the rotor, so omega. So omega. So simply this means that the angle between here and here is what? Is theta r. Why? Because AS is stationary. The stator is never rotating. The stator is stationary. The rotor is rotating. So theta r actually is equal to what? The integration of omega r d tau plus theta r of 0 if I'm having initial condition. Because in the end of the day, I don't know where the rotor will stop. Yes? So I will have initial angle. Huh? Later on, for simplicity, I will assume the initial angle is equal to what? 0. Good. Good. So I I need to find a mathematical model that represents this system. So if I need to plot it as electrical circuit, simply I will have resistance and inductance to represent each coil. So let's assume that this is the plus, the minus of VES. So this will be the RS, this will be the NS. Now the R is what? RS is the stator resistance. NS is what? The number of the turns. But simply here I will not say the number of the turns, I will say the effective number of the turns. Because not all the turns of the coil will be participant in generating the flux. There's a leakage of flux, there's a magnetizing flux. So let's assume this NS is what? Is the effective number of turns. So here I'm plotting the stator side. Yeah? Let's assume that this is the B. So this is the VBS. And this is the VCS. So here IAS will flow, IBS will flow, and ICS will flow. Now the same thing, I'm having one for the rotor. Let's assume it's here. So this will be the RR, this will be the NR, and the same thing, let's assume that this is the IAR, this is the IBR, and this is the ICR. So this will be plus and minus VAR, this will be the plus, the minus VBR, and finally the plus and the minus of VCR. Okay. Having two. I'm opening two. Okay, that's right. I'm having to duplicate both. Why? Why am I having to duplicate both? Okay. This one and this one. So let's turn off this. This one, let's turn it off. Great. So I will have this one. Because I was searching for the hand. There's no hand. Okay. Good. Now I need to represent a mathematical model for the stator circuit and for the, let's say, the rotor circuit. So this is the stator and this is the rotor. And as we said, S stands for the stator and R will stand for what? For the rotor. And to make the discussion very simple, I will say that IA or IKS, let's say. See? IKS, where K can be A, B, or C, is the stator current. Correct? Yes? And the same thing I can say VKS, where K element ABC is what? Phase voltage, huh? Is the stator phase voltage. Now the same thing, I can say that IKR will be what? And VKR will be what? Yeah. So instead of writing, let's say, 3 equations, I can write single equation. Yep. Good. And also, I can use the film notation F, A, B, C to represent a vector of F, A, and this is Fs, this will be the S, F, B of S, F, C of S. Yep. Where F here, F can be any function. So let's assume it can be voltage, it can be current, it can be flux, for example. So simply, if I'm saying that VABCS, this will equal to what? VS, VBS, VCS, no? So sometime we'll say that for the space, I will say VAS, VBS, VCS, and here I will use what? Transpose. Yeah? So this is only what? A way of writing the thing, yeah? A way of writing the thing. Now the same thing I can say FABCR will equal to FAR, FBR, FCR. Yeah? Good? Okay. So now I will try to write the voltage equation in the machine diagram. Let's try to write the voltage equation in machine diagram. What's the meaning of the machine variable? Here, the voltage equation machine variable, I mean that I need to write the voltage equation in terms of the current, in terms of the voltage, in terms of the flux, and in terms of theta or omega, correct? Those are the machine variables, correct? Good. So now, if I'm having RL circuit, how I can write the voltage equation? Go back to the circuit, the fundamental of the circuit. If I'm having RL circuit, I need to write the voltage equation. You will say what? So you will say that what? The summation of the voltage around any closed path must equal to 0. Then you will say that Vn must equal the drop voltage across the resistance and blah blah blah. Correct? So actually, this is the same. We will do the same, except that we will return back to Ohm law and Henry law of induction. Yeah? From Henry law of induction, actually, you find that VL is equal L di by dt. Yep. Yeah? So simply here, we will say that the VABCS will equal. Now, I'm having RS, which is the resistance, and this is the matrix. Now, IABCS plus the d by dt of lambda ABCS. The same thing we can write for what? For the rotor circuit. VABCR will equal RR IABCR plus d by dt of lambda ABCR. Now, this one is what? It's Ohm law. Yeah? And this is what? This Faraday law of induction. Because the Faraday law of induction.
اللمدة هي الفلكس.
Flux linkage, yeah. So, if linear, this will be Li. And if the inductance is constant, this will be L di by dt. Huh? Now here we discover that in the machine, the inductance is very important. It will be time varying. And due to the time varying, I will generate something called what? Developed power. Otherwise, I cannot generate any power. Correct?
ليش ما كتبناها بدلالة الامبيدنس؟ بس IABS times ZABS.
Now the impedance is equal to what?
plus
Plus what?
J omega.
L.
L.
Now, if L is time varying, how can describe the impedance there? Now, until now, we don't have any relation for the inductance, by the way. We only say that I'm having a coil. So if I'm having a coil, if I need to write a voltage equation, then I will say that I need to use the Ohm law because any coil has a resistance, correct? Then I need to study the rate of change of the flux linkage. Yes? Yeah? So the first one is the Ohm law, the second one is what? Is Faraday law of induction. Now if lambda for linear magnetic circuit, it will equal Li. For linear magnetic circuit, for sure, it will equal Li. Now if the inductance is constant, I can take it out from the differentiation. Yeah? So in this case, I will get what? What I know, VL. Yeah? L di by dt. But if this is the case, then where's the developed bar? In the end of the day, if I multiply this one by the current, here I will get what? The ohmic losses.
Yes.
And here I need to get what? The combination of what? Of the power. Yeah? The rate of the change in the field energy, I need to find the power that converted to the mechanical energy. So this means that the secret will be here in the inductance of the machine. Yeah? In the inductance of the machine. And this is the topic of our course, or this lecture, by the way, how to find the mathematical model of the machine. So we said that the first one is the Ohm law, and the second one is the Faraday law of induction.
يعني دكتور احنا نشتغل بالنون لينير ريجن.
No.
إذا كانت لينير ستيدي ستيت المفروض تكون زيرو.
You are missing the point. For a linear magnetic circuit, the meaning is what? If this is the I and this is the lambda, or the BHK, this is what? Linear magnetic circuit. Yeah? This is what?
Similar.
There's non-linear. There's no semi-linear. There's non-linear. Yeah? The non-linear magnetic circuit. Now, in general, we are designing the machine such that it is within the need of the non-linear in order to maximize the capacity of the machine. So, in the end of the day, I can assume that the relation between I and lambda is what? Is linear, which means that lambda can be described as Li.
والفاضل بالمثال.
إيه؟
لا جزء معين بس بتكون لينير.
I think I said that when we design a machine, we will design the machine such that we are operating in the knee of the end of the linear region in order to maximize the capability of the machine, which means that I can assume the relation between the I and the lambda to be what? To be linear. Good. But after that, I will discuss the both case, the linear and the non-linear, and at the end of the day, I will get the torque expression for the two to be identical. Good. Good. But simply this means not constant the flux. If the flux is constant, then simply, if lambda is constant, the d by dt of lambda will be 0. Correct? Yeah? This will be what? At steady state. Now the mathematical model will discuss what? The transient and the steady state. Yeah? Even in Laplace, by the way. Even in Laplace, you have a transient, let's say, period, and you have the steady state. Good. So now let's see. The voltage, we know, VABC, we know it. Why? Because we are giving the voltage to the stator, and for the rotor it's equal to what? 0. Shorted. If I'm using a squirrel cage, it will be shorted. If I'm using one rotor, I'm shorted, then it will be shorted. Now, in order to proceed, I need to find an expression for what? For the flux linkage. Yes? Okay. So now let's see. So I need to find an expression for the flux linkage, which is the lambda ABCS, and also I need to find an expression for lambda ABCR. Now, the flux linkage in the stator is caused by what?
In the stator.
And the flux is caused by what?
Magnetization.
Current. By current. So, the flux linkage in the stator will be caused either due to the current flowing in the stator or a current flowing in the rotor. Correct? So this one has two parts. Yeah? I will say that this one will have, which is the flux linkage, lambda ABCS due to the current in the stator, plus lambda ABCS due to what? To the current in the rotor. Correct? And the same thing is valid for what? For lambda ABCR, correct? Lambda ABCR due a current in the stator plus lambda ABCR due a current where? In the rotor. Now here, for linear magnetic circuit, we can assume that lambda can be described as LR, correct? So simply this means that lambda ABCS and lambda ABCR will equal to certain matrix multiplied by the currents. The first one is the IABCS, and I'm having IABCR, correct? Now I need to put a tag or a name for the inductance. The first one is what? This one is what? This one is the inductance due to what? So simply if I need to find LS, it will be lambda ABCS over IABCS, and this will be due to what? To the stator, correct? Yeah? So this will be LS, the stator inductance, correct? Which is what? Is the inductance due to current flowing only on the stator, correct? Then I'm having what here? This one. This is a coupling, correct? So this will be the LSR, the inductance as seen between the stator and the rotor. Now this will be what?
LRF.
So it will be LSR transpose. Yeah. Instead of writing 3 matrices, I will write 2 matrices. Instead of writing LSR and LRS, I will say no. It's LSR and this one the transpose of that. Yeah? So the last one here is what? LR. Good. So now let's try to find the first one, which is the self-inductance. Huh? So now let's try to write LS. LS will equal to. Now LS will be 3 by 3. Just why? Because I'm having 3 by 3, 3-phase system. 3 by 3 system. So the first one is L. What and what? So this one is LAAS, which is inductance caused by current flowing in phase A, affecting only phase A. Correct? Yes? So the second one will be what? LABS. Correct? LABS. So this one, the inductance as seen in phase A due to the current flowing in phase B. Correct? The third one will be what? LACS. Correct? So writing the names is very simple. Giving the tag is very simple. So who can give me the second one?
LBAS.
Then? LBBS. Then? LBCS. Who can give me the last one? LCAS, then LCBS, then LCCS. Correct? Yes? Okay. Now those are what? The diagonal. Those are the self-inductance. Correct? So those are what? The self-inductance. So what about those?
Mutual.
The mutual inductance. Yeah? Those are what? The mutual inductance. Good. Which is the stator mutual inductance. Okay. Now I need to calculate those. So I will start with the stator self-inductance. So I will start with the stator self-inductance. Now, any self-inductance is decomposed of what? Or any inductance is decomposed of what? If I'm having a coil, if I'm having a coil and there's a current flowing in this coil, it will generate two fluxes. Yes? One is what? Is the leakage. Leakage, because, okay, not the self, because the leakage. The leakage inductance, and the second one is called the magnetizing inductance. What's the difference between the leakage and the magnetizing? The leakage is only cutting or interfacing with the coils of the current itself, while the mutual is interacting with all the coils. Yeah?
Yes.
Example, if I'm having here a coil, and here I'm having another coil, and there's a current, here I will generate a flux. Yeah? So part of the flux will interact here, and part is only interacting here. This one is the leakage. It's only interact with the coil itself, while the magnetizing is interacting with all the coils. Yeah? So similarly, this means that the LAAS will equal to LLS plus LMS, where LLS is the leakage inductance and LMS is what? Is the magnetizing. So the same thing here, LBBS will equal to LLS plus LMS, and finally LCCS will equal to LLS plus LMS. Where the LLS is the leakage inductance, and LMS is the magnetizing inductance. Good. Now, what about the LABS, LACS, the stator mutual inductance?
LMS.
LMS only, huh? Okay. Now see. I'm having three phases, correct? So simply this means that here I'm having AS, here I'm having BS, and here I'm having CS. Now LABS is what?
3 LM.
Just fluid, yeah? Or let's discuss this one. Maybe it will be more projecting, huh? LBAS is what? A current flow where? Where? So if a current flow here, this will project a lambda here. Where I will see it?
B.
It's a B. So I will see it here. So I need to project it. Yeah, I need to project it. The angle between A and B is what? 120 degrees. So it will be the LMS cosine the 120. Yes? Yeah, of course it will be LMS, but there's an angle, you know? So this means that all the stator mutual inductance, LABS, LACS, LBCS, LBAS, LCAS, and LCBS are equal, which equal minus 1 over 2 LMS. Why? Because cosine 120 degrees is minus 1 over 2. Okay. So let's write it here. So this will be the LABS will equal to the LBAS, which will equal to the ACS, which will equal to the LCAS, and finally I'm having the LCBS, which will equal the LBCS, and this will equal minus LMS over 2. Do you see from where 1 over 2 coming from? Okay. So if I'm having 5 phases, the angle between the axes will be what? 62. Yeah? 360 over 5. 72, sorry. It will be 72. 60, 70. 70, huh? Not 72. Yeah? So in this case, I need to project by which angle? Cosine of the 72. Yeah? If I have 9 phases, it will be 360 over 9, correct? So this angle decided by what? By the phases. Yeah? By symmetry, I mean the phases are symmetric. And in this course, I'm discussing only a symmetric machine. Huh? Okay. And we know that the LMS actually, LMS will equal the NS square over the reluctance path, RM. If I need to calculate it, it will be the stator, the effective turns of the stator square over the reluctance path. Good. Now, what about LSR? So let's try to find the LSR. So, if you remember, lambda A, B, C, S due to the rotor. So can be written as, here the current is what? Which current here I'm discussing? The rotor. So this will be the IAR, IBR, ICR. So this one will be the inductance between what and what? AS, AR, correct? The current. So the first suffix, this one, where I'm seeing the inductance. And the second one is what? Where the current is flowing. Good. So in this sense, this will be what? This will be the LAS BR. So this will be what? LAS CR. Who can give me this one? Yeah. So it's very simple, huh? So this will be the LBS AR, LBS BR, and LBS CR. The last one? LCS AR, LCS BR, and LCS CR. Correct? Yeah.
دكتور ليش ما حكينا ال A AR؟
Because here I'm having stator and rotor.
طب قبل مش كان عندنا كمان؟
That's stator. Before I'm having stator, correct? This one, stator and stator. So I can write LAS.
طب ليش هون ستيتر وهناك ستيتر؟
Here I'm discussing this one.
اوكي.
Yeah?
تمام.
I'm discussing previous. Next one.
Next.
So I did 2 next. Jump in time. So here I'm writing lambda A ds due to what? The rotor. And here is what? Is the rotor. Yeah? So I'm trying to find the first one is ls, the second one is lsr. Yeah? So this will be what? This will be what? The lsr. The mutual inductance between the stator and the rotor. The mutual inductance between the stator and the rotor. So this one is the mutual inductance between the stator and the rotor. Good. So now let's see. So simply here I'm discussing what coupling between a fixed frame and rotating frame. Correct? So let's assume that this is the AS. Let's assume that this is the BS, and let's assume that this is the CS. And I will plot the R axis, so this is the AR. So this, not the same angle, of course, it must be the same. Almost the same. This will be the VR, and now this will be the CR. Yeah? Now remember, the rotor is rotating by which speed? Omega. So this will be theta, right? This angle is what? Theta. The angle between AS and AR is theta. So the angle between BS and BR is the same. And the angle between CS and CR is what? Is the same. Yeah? Of course, this one is appear to be higher, but simply I'm not Picasso. Yeah? This is the best that I can do. This is the theta. If someone say no, say yes, it is theta. Huh? Good. Now the rotor is rotating. Okay. Now let's see. The angle between. Okay. Now, if I'm having inductance, if I'm having 2 inductors, let's assume I'm having this the first one, and this the second one. Roughly, imagine that I'm having 2 inductors. Now, if they are elegant to each other, which means that the flux will be supported, huh? Then I'm having the maximum coupling. Yes, I'm having the maximum coupling. So I will assume that the maximum coupling, I will call it LSR. So I will call this one, in this case, I will call it what? LSR. LSR. Now, if the rotor is rotating, imagine that the rotor become here. And the stator was here. Now, the coupling in between are the same? No. Yeah? It will be what? Projected by which angle? By the angle between the stator and the rotor, correct? Yes? Good. Now let's see. So, the angle between AS and AR, theta, the same angle between the B's, and the same angle between the C's. So this means that LAS, AR will equal to LBS, BR, and it will equal LCS, CR, which will equal to what? LSR, the maximum coupling, cosine the angle in between, which is theta. Thank you. So you get the concept how I'm calculating the inductance. By the way, this is only valid for cylindrical rotor. If the rotor is not cylindrical, this is not valid. Yeah? But simply because the rotor is cylindrical, whatever the rotor is rotating, the gap is uniform. So the reluctance path is not changing. If the reactance path is not changing, I can rely upon that. Otherwise, I should need to do 3 steps. The first thing, I must generate the MMF at the axe. I need to project it in the second axe I need. Then I need to generate from there the flux linkage. Then I need to project it back. Then I need to divide it over the current to find what? The inductance. This, if we have the time later on, I will discuss it for what? For the non-uniform, let's say rotor, or what we call it, salient. Salient rotor. Yeah.
دكتور الثيتا ار بتتغير صح؟
Yeah, theta r is changing.
Changing.
But whatever theta r is changing, I'm having cosine theta r. So if A, S, and A are elegant to each other, I'm having the maximum inductance. If they are 90 degree, I will have what? Zero inductance. Yeah? But whatever they are changing, I'm capturing this thing. Huh? So this will give a first clue. The mathematical model will be time varying. Because the inductance is time varying, correct? Yes? So this means that the system is nonlinear. Because if the parameter is changing with time, this will destroy the linear invariant system. Huh?
شرط دكتور لحظيا يعني في قيمة LS تفرق كل ثانية تكون لها قيمة معينة.
Yeah, of course, the rotor is rotating. Yeah?
يعني
All the time it's rotating.
كل لحظة لها قيمة معينة تفرق على.
Yes, and actually, if the inductance is constant, the machine cannot develop a torque. So later on, we will derive a mathematical model for the torque. We will appreciate the time-varying nature of the inductance. In the machine, in the electrical machine, I must preserve 2 conditions for the machine to rotate. The first one, I must have air gap. Without gap, the machine will never rotate. That's why the gap is very important. Yes? Even though the higher the gap, the weaker the machine. So I must have what? A very small gap in order to allow the machine to rotate. Otherwise, it will be impossible to rotate. The second thing, I need to have inductance varying with time in order what? To generate a torque. Otherwise, I cannot generate a torque.
يعني دكتور الديفلوب توك بيكون FT 0.
No. No. Later on, we will discover that the developed torque has a relation with the field energy. The field energy. So in the DC machine, for example, or the, let's say in the steady state analysis, we give you that the torque is proportional with the flux and IF. But from where? Why? Huh? And simply in the DC machine, we say that we need to have brushes. Yes? And those are brushes is fixed to what? To specify the axe of the induced voltage, correct? That to maximize the torque. In order to maximize the torque. Yeah? We make it 90 degrees. This is the maximum. Yeah? So here I will try to solve, or let's say to answer some of the basic questions. Yeah? So this is what we call the raw of the machine. I'm dealing with the machine from the scratch. Yeah? Without any knowledge, just only the circuit. I'm trying to build a mathematical model from our analysis of the circuit. Later on, we'll develop a torque for that.
دكتور يعني احنا مش بالبي اتش كير كانت in some point will go
Saturation.
constant saturation mode يعني إذا هيك بصير عندنا الاندكتنس constant تصير هاي يعني هاي الريجن.
No, just a minute. Zero. Now, the pH curve, yeah, the pH curve is the relation between the flux and the, let's say the current and the flux linkage, or between the flux density and flux intensity. Good. Now, any physical system cannot hold the flux forever. It will be saturated. It will be saturated. So, when the flux is saturated, this means that if I increase the current, nothing I can change in the inductance, which means that I'm consuming more power that I need. And I think we discussed that somewhere in the class, I think. Yeah? In the view of valve control, why we cannot reduce the frequency while the voltage is constant? Because the flux will increase. Someone said, yes, the flux is increasing. I'm happy because the torque will increase. You say, no. Why? Because at certain sense, the flux will never change, so you are consuming current that you never need. Yes? So if you are consuming current, this will be dissipated as well heat, as magnetized, as losses in the core. Core losses, yeah? Yep. Okay. So if this is the case, who can give me LASBR? This one. So the angle between AS and BR is equal to what?
Theta.
Yes, so theta R plus 2 pi over 3. Yes? Is it the same as BS and CR?
Yes. Yes.
So BS and CR. BS, and CR. This one. Is it the same as CS and AR?
Yes.
Yeah? So what is it? CS and AR. So they are the same, huh? So I will say that LAS BR will equal to LBS CR, and it will equal to LCS AR, and this will equal to what? LS R cosine what?
Theta R plus 2 pi
Yeah, thank you. Plus 2 pi over. Now what about this one?
minus 2 pi.
So the relation between AS and what? And CR, this one. This angle. Equal to what? 2 pi over 3 minus theta. The same as this one? The same as BS and AR?
Yes.
Yes. The same as this one?
Yes.
Yes. So I can write that L I can write L BS AR equal to L AS CR equal to L CS BR, and this equal to what, Joel?
LSR
LS
cosine theta R minus 2 pi.
Cosine?
Cosine theta R minus 2 pi over 3.
No, 2 pi over 3
Okay.
minus.
Jamal is very genius, by the way. He said that cosine of theta is equal
minus
cosine of minus theta.
theta.
That's all. And here, by the way, C is for the cosine, because I'm too old to write cosine was C. Good? Yeah? Yes. So now what I need, I think I finished everything, huh? So until now what I'm having? Until now I'm having the LS, and I'm having LSR, so for sure I'm having the SR transpose. So only I need to find LR. LR is equal to what? The most laziest formula you can find. LR equal LS such that S goes to R. Yes? LR will equal to LS such that S go to R.
Yes. Change this, but
Yes. Yeah? So simply here, if I came back here, what is it? Huh?
Which is LSR transpose.
No, this one. You see the LS? This LS, so this will be LR equal LAAR, LABR, and so on. So here, this will be what? LAAR equal LLR plus LMR. Yeah? Or should I write it? Should I write it? Okay, let's try. So to this end, what we have? To this end, we having the LS can be written as the LS plus LMS on the diagonal, correct? And here I'm having what?
Minus.
LR equal to what?
كان أبدل كل الاختيارات.
So
تصير الأسلم.
then
كمل نفس الشيء. MR over 2 بعدين minus LR LMR over 2 كمل.
yeah. Good. Now what about the LSR? This equal to what? Yep. So this will be the LSR here, and here I'm having what? Cosine
Sin
theta r, then cosine theta r plus 2 pi over 3, then cosine theta r minus 2 pi over 3. Here I'm having cosine theta r, here I'm having cosine theta r, and here C stands for what? For the cosine. Here I'm having what? Cosine theta r minus what? Cosine theta r minus 2 pi over 3. Here,
cosine theta r plus 2 pi.
so cosine theta r plus, so cosine theta r plus 2 pi over 3. Here I'm having cosine theta r minus theta r minus the 2 pi over 3, and here I'm having the plus cosine theta r minus the plus, sorry, 2 pi over. Now, LS, LR are constant matrices. Constant matrices. They only depend on what? On the geometry. Geometry. The magnetizing path is the geometry. Correct? What about LSR?
Time.
Function of theta. So it's a function of time. Correct? So LS, LR is constant. Why? LSR, this matrix, is a function of what? Of theta r. So this means that LSR is time varying. Correct? LSR is time varying. Okay. Now it's preferred to write all the quantity referred to the stator, and to use LMS instead of LMR. We have a relation in between. So simply here we can say that LSR actually is equal to NR over NS LMS. So instead of this one, I can write the NR over NS LMS. The same thing I can do here. And the LMR also, this one, can be described as, in terms of the term ratio, as NR over NS squared LMS. So I only need to refer the rotor to the stator, and this is also, we do it all the time in order to find the equivalent circuit. So if we refer the rotor to the stator, now we know that I A B C R dash will equal to NR over NS I A B C R. So the voltage as referred to the stator V A B C R dash will equal to what? Why NS over NR, not NR over NS value?
IDA CE.
Huh? Why? Why this one in R in S and this one in S in R?
لأنه فولتج وكرنت.
ليش؟ To preserve the power. Yeah? I dash V dash must equal IV. Yes? Otherwise you are shaping the power and this is impossible. You are speaking about something else. To preserve the power. The flux linkage is following actually the voltage. So lambda AB CR dash will equal to NS over NR lambda ABCR. So if I need to refer the rotor VABCR, which will equal to RRIABCR plus D by dt of lambda ABCR. What I should do? I need to refer, so I'll multiply the both by what? So NS over NR. If I do this, so this one automatically will be VABCR dash. Yeah? Now here what I'm having, NS over NR, RR. Now this one I need to refer it, so I will use what? The reverse of this one. Huh? So simply here I will say that the IABCR equal NS over NR IABCR dash. So here I will put what? NS over NR IABCR dash, and here I'm having plus NS over NR d by dt, and here I need to refer it, correct? So I need to use the NR over NS lambda ABCR dash, correct? So here what I'm getting is the referred resistance. Huh? So RR dash will equal to NS square over NR whole square. Huh? Yes, so until here we have a voltage equation. Until here we have what? The voltage. So until here we can say that we can write it in matrix form as VABCS VABCR dash, which will equal to, this will be RS plus D by dt of LS D by dt of LSR dash D by dt of LSR dash transpose, and this will be the RR dash plus D by dt of LR dash multiplied by the current. Well, those are IABCS IABCR dash. Now, you know this one. This is a differentiated operator. Anything coming to it, it will differentiate. So it not only differentiate the L, it will differentiate the multiplication of L and the K. Huh? Understood? Okay. So, until here, I'm having the voltage equation. For the mechanical part, we note the swing equation is sufficient to describe any rotational system. Now, what I need, the coupling in between. Yeah? I need to find a relation that will couple the electrical system to the mechanical system, which means that I need to find a relation for the electromechanical torque in terms of what? Of the machine variable. In terms of what? Of the machine variable. Okay. How we can do that? I need to find out the torque expression. How I can do that?
Swing equation.
No, for the mechanical part, I know J d omega by dt plus b omega must equal the summation of the torque, which is TE minus TL. Now the missing is TE. Yes? I need to find an expression to describe what? TE. I need to find an expression to describe the electromechanical torque in terms of machine variable, which means that the current and what? The theta. Or the flux and theta. But in general, we describe it in terms of what? the current. Because we can measure the current. The flux is difficult to be measured. Yeah? Okay. How we can do that?
PD root over omega.
Where's the beat of load? Where's the beat? Now, let's return back to the initial stage of Faraday and Henry. They said that if you are imposing a voltage, a current will flow. Yeah? Now, if we assume that no mechanical power is allowed, no mechanical work is allowed, and R is go to 0. So simply this means that V will equal to what? According to Henry law of induction, I d lambda by dt. Yes? Yeah? Now, if there is no mechanical power, and if there is no losses, then if I increase the voltage, I will increase the stored energy. If I reduce the voltage, I will reduce the stored energy, correct? Yes? There is no mechanical power, which means that I'm fixing the rotor not to rotate. It's impossible to rotate. And I'm assuming that R is negligible. I'm not interested in the ohmic losses. So any change in the input must appear to be stored in the field energy, correct? Either I'm increasing the field energy or I'm reducing the field energy, correct? So I d lambda by dt, which is the input power, will equal d omega f by dt. So from here I can say that I d lambda will equal d omega f. Yes or no? Yeah, from here. Multiply by dt. The variation. I mean the variation. D lambda actually is d by dt. So now let's see. Let's discuss the two things. If I'm having linear magnetic circuit, then if this is the I and this is lambda, I d lambda, what is it? I d lambda, you know that. If I need to find omega f, I will integrate, correct? If I need to find omega f will equal to what? The integration of I d lambda. Yes? Now, integration of I d lambda is area under a curve. Where is it? The upper area. So thank you. So this means that if this is the I and this is the lambda, I1 lambda 1, this will be omega f, correct? Yeah? Now someone will say, if you have two areas, the second one will be the complementary area. So the second one I will call it omega c, the co-energy. So the first one, omega f, is the field energy. So the second one, the field energy has a meaning, has a physical meaning. The co-energy has no meaning, but it will be very fruitful when we derive what? The mathematical expression for the term. It's the complementary area. Yes? So this one is the field energy. So this one, this blue. So this one will be what? The co-energy. So I will call this one omega c, while the first one I will call it what?
Omega.
Now, if this one is non-linear, it will be the same, yes or no?
Yes.
It will be the same, correct? This will be the field energy, yes? And this will be the co-energy, yes or no? Now, whether it is linear or non-linear, the summation of the field energy and the co-energy will equal I lambda.
Yes.
Yes, correct? Huh? So I lambda will equal to what? Omega f plus omega. Correct? Yes? Good. So now let's return back here. If I'm allowing the coil to do a mechanical work, then in this case, I d lambda by dt will equal d omega f by dt plus the mechanical power. Correct? Yes? Now, if I'm allowing So if the coil is allowed to do mechanical work, then I d lambda by dt will equal d omega f by dt plus the mechanical power, correct? Yes?
Yes.
Now the mechanical power, it is the force. If I'm, or for you, I will discuss the torque directly. You know that in the linear system, I will generate force. In the rotation, I will generate what? Torque. So the mechanical power will be what? The torque multiplied by omega. Yeah? So, so it will be TE d theta Rm by dt. Yes or no?
Yes.
Good. Yes? Yeah? So simply this means that here, from here I can rearrange the equation and say that d omega f will equal I d lambda minus Te d theta Rm. Correct? Yes?
Yes.
Good. Now, please pay attention to what I will do. If I'm having I lambda here, and I'm having this one. Now, you know that if theta is changing, this is valid for certain theta. If the inductance is changing, remember the inductance? LSR was changing. And the slope of this relation is the inductance value. So if theta r is changing, this means that this curve is not valid. I should have another curve. Correct? Yes? Yeah? So let's assume at certain time, I'm having theta 0. So if theta is changing, I will get another curve. Let's assume here. Correct?
Yes.
Theta r. So this means that the field energy is changing or fixed?
Field energy changes.
It's changing. And the core energy will be changing. Okay. So this means that the field energy is a function of what?
Theta.
Huh?
Theta.
Theta. Yeah? Yeah. So this means that omega f is a function of theta r, and it's already a function of lambda from here. Yes? Yeah? Yes? Good. Now, who can differentiate this one? Who can find d omega f equal to what? Partial. By d, yeah. Partially. Yeah, partially. Partially. No. Go. ركنية من مكان خطير بقول لك واحد.
قول دي باي دي ثيتا
ايوه.
بلس دي باي دي اوميجا.
شو هذا؟
تشتغل بالنسبه
chain rule. I will use the chain rule. ها؟
الأول في مشتقة الثاني
الأول في مشتقة الثاني زائد الثاني في مشتقة الثالث، خذ الليمت بيطلع صفر على طول. So this will be partial omega f by partial lambda. Yeah. Good. This is the first one, huh? D lambda plus the second one, partial omega f by partial theta r d theta. Good. Okay. Now, you know that if I need to do the partial derivative, I will fix the other value, yes or no?
Yes.
So the first one here, when theta r is constant. If I need to evaluate, I will assume theta r is constant and I will differentiate. And this one,
لامدا
when lambda is constant. Correct? Okay. Now, do you see this one? Huh?
yes
And do you see this one?
equal
They are equal, of course. So from here, I will equal to what?
D omega
دي اوميجا
باي
باي دي
دي
باي دي
when theta r is constant. And the torque will equal to what? Minus.
دي اوميجا ار اوفر
So simply someone will say from here I can find the torque which will equal minus partial omega f by partial theta rm, of course, huh? Because here it will be the m, huh?
يس لامدا is constant.
Yeah, when lambda is constant. Good. Now, what about if I need to find the co-energy? So someone will say if I'm having the field energy, I will differentiate the field energy with respect to theta, and I will find the mindset will be what? The torque. Now, what about the co-energy?
لامدا اي ناقص
What about the co-energy? And you see this one? If I differentiate this one, if I need to find di lambda, this will equal to what?
دي بلس دي اوميجا
So it will be lambda di plus I d lambda, correct? The chain rule. Yeah? Yeah? Good? Good. So simply someone will say, if you have d omega f, the d omega f is equal to what actually? It was what? I d lambda. Yeah? So this one is d omega f. Yes?
يس
So simply I can substitute from there and replace the variable from omega f to omega c, correct? Yes? So I can do that. So I can say that omega c will equal to I lambda minus omega f. So d omega c will equal to what? Lambda or I d lambda plus lambda di minus d omega f. D omega f we have it, this one. So I'll put it here. If I do so, what I will have?
اي دي لامدا
The first I d lambda will be what? Eaten, according to the Bachmann theory. Look. So I d lambda will be out, so this will be lambda di plus.
يس
Okay. So plus, huh? Plus. Plus te
دي ثيتا
d theta rm. So the same thing, if I recall back here. Omega c actually is a function of what and what? Theta and I. Yeah? Theta. So from here also, I can say that omega c is a function of theta and I. So let's differentiate it. So if we differentiate this one from here, we can see what? So this will be partial omega c by partial I di plus partial omega c by partial theta d theta.
بس واحدة ثيتا كونستانت واحدة اي كونستانت.
Yeah, of course. Thank you. So here, here is what constant?
ثيتا
Theta is constant. Can you see the yellow? I'm shaving. And this one's what? Huh? This I is constant. Okay. So from here, I can say that from here, if I compare, then the torque, which I need, is this one. Yeah? So this means that the torque will equal partial omega c by partial theta m when I is constant. مين حكى انه constant I constant؟ انت صح؟ شو اسمه؟
ابراهيم.
ابراهيم. Actually the current is not constant. Actually theta is not constant. Yeah? Actually the flux is not constant, صح? But those are not physical requirements. Those are mathematical requirements. Yeah? Only I need to think they are constant in order to do differentiation. Otherwise, I cannot do that.
اصلا اول شيء حكينا انه الاو بالميكانيكا يعني هي اصلا يرجع ماثيماتيكال انه نطلع الدور.
لا.
فعليا ما في دور.
You know, the first stage, in order to tell you that the input power will be divided in two powers. One is stored in the field energy, and the second one is converted to mechanical power. Of course, I have the third one, which is the losses. But here I neglected it, because I only need this one, because I link it with theta. The ohmic losses will never contain theta inside. Yeah? So if I need to do the chain rule, I must think that all the other variable is constant, although they are not. Otherwise, I cannot do the differentiation. صح?
يعني هو assumption
Simply, if I'm telling you xy, find d by dt of x, where x and y is time varying. كيف بتحلها؟ بتقول x y dot plus y x dot. So you are thinking in the first stage that x is constant, and you are differentiating with respect to y. Then you will say no, y is constant and differentiate.
بس هم الحقيقة مش تبع.
Yeah, of course. Physically, they are not. So here, it's a mathematical assumption that I'm assuming in order to do the differentiation. Otherwise, I cannot do it. Okay. So now, someone will say, if I'm having the field energy, then I can calculate the torque. Yes? Good. The field energy from circuit 2 or 1, I don't know. The field energy of two coils equal to what? The field energy. And I will stop after that. If you have two coils, and this is L1, this is the L2, and here I'm having M. And here I'm having I1, here I'm having I2. Then omega F will equal to 1. You will say 1 over 2 L1 I1 square plus 1 over 2 L2 I2 square plus M I1 I2. So, yes. Here are the same. Instead of that, I'm having a set of coils on the stator and set of coils where on the rotor. Correct? So who can give me the field energy?
in the state.
No, in the machine. So you say that omega. Now this one, assume it is the stator. So you will say that this one will equal I, A, B, C, S, transpose, L, S, I, A, B, C, S. You should respect that you are multiplying now matrices. I cannot multiply a column vector on a matrix. Yeah? Unless the column vector become after the matrix. Yeah? Then I need to add 1 over it, 1 over 2. Yeah? So this will be 1 over. Yes? Plus, who can give me this one? 1 over 2, the I, A, B, C, R dash transpose, in R dash, I, A, B, C, R dash. Yeah? The last one, who can give me the last one?
I A B C S plus
I don't have M, I have LSR.
I A B
CS I B C S
مرة ثانية معلش.
I A B C S
Transpose.
yes ضرب I B C R
Dash. So simply you say that it will be I, A, B, C, S transpose LSR dash, and here I'm having the I, A, B, C, R dash, correct? Yeah? This is the mutual, coming from the mutual. Now let's see. Which one I will use, the field energy or the co-energy in order to find a torque? يلا.
Field or
أو co-energy, يعني أوميجا سي ولا أوميجا أي واحد بختار. We did not discuss that صح؟
الكو انرجي احنا حكينا انه in terms of theta and I. هون عندنا I فبنسوي I نفرضها constant فبنقدر نعمل كو انرجي.
Yeah, he's very genius. Actually, if I need to use the field energy must be described in terms of flux linkage and theta. And it's very tough, by the way, to find it here. But if I'm having the co-energy, it must be described the current and theta, and I have it. And for linear magnetic circuit, omega C is equal to omega F. Yes?
Yes.
Yes? So simply for linear magnetic circuit, we can say that omega C is equal to omega F. So now I can find the torque which will equal partial omega C by partial theta R. أعطيني هنا.
partial omega C.
Now this one contain any theta R inside it?
No.
So I don't need to differentiate this one. This one? No.
theta لا.
So only I need to differentiate this one. Now I'm differentiating with respect to what? To theta.
Theta.
So this will be the IABC as transpose partial LSR dash by partial theta R IABCR dash, and what's the relation between the electrical variable and the mechanical variable?
Turns ratio.
So this will be P over 2.
Yeah.
Because LSR is function of theta R, not theta R mechanical.
Yeah.
So now what I need only to go to the LSR, differentiate, multiply it, and some write it to find the torque expression. Yes? Good. So I'm finishing the mathematical model right now. Huh? This is only the mathematical model. So I will stop here. So next time we'll discuss why the mathematical model in the machine variable is so difficult to deal with. In general, if I need a mathematical model, why I need a mathematical model? ليه؟
To simplify إنه نفهم كيف
Yeah, to understand how the machine is working. Thank you. ليك علامة على ذلك the first thing. The second thing is to design a controller for the machine based on the simulation. صح? Now see, the mathematical model itself is time varying. And until now, unfortunately, we don't have any tool to deal with a time varying differential equation. The second thing, the torque expression will be what? 20 terms. Maybe. And you don't know where you should modify. For example, in the DC machine, it was very straightforward. I know that if I need to control the torque, I need to control the armature current. Here, if I need to control the torque, which current I need to control? How to control it?
State or motor.
So so this one is very difficult to deal with. So in the end of the day, I need a mechanism, a transformation in order to simplify the understanding and the control. Yes? So this means that in the end of the day, I need to have a certain transformation in the same concept of Laplace. Not Laplace, of course, but Laplace find a method in order to transfer a differential equation or dim differential equation to algebraic equation. Here, we will have another transformation in order to transfer a time varying to non-invariant system. Yep. شكرا. يعطيكم العافية.